Father, we thank you for this class. We start this class in your name, O Lord. Amen. Um, so now we would be so this is our first lecture on Maths 122, and we would be starting with limit and continuity. Limit and continuity. So we would be treating limit and continuity. Now, what's the entire concept on limit and continuity? Now, this quite very simple. Okay, we would be starting from the basics and we would be going to more the advanced stuffs. Now, a limit describes the value of a function or a sequence as it approaches a particular value. Like that's the basic definition of limits. So as it approaches a particular value, right? Then we get a limit. Okay, so it's kind of makes sense. Like it's just a play of words. Okay. So now let's take this example and let me use this example to explain it much better. Okay. So now having the limit, right, as x approaches 1, right, of the function x squared on x squared minus 1 on x minus 1, right. Now we can see that when we input in 1, right, we get an undefined value, because when we input in 1 we get 0 on 0, right. So this actually is undefined. 0 on 0 is not equal to 0. This is undefined. We would be treating all undefined forms in other lectures, okay, but this is basically an undefined value. So we know that at 1 in the graph, x squared minus 1 on x squared minus 1 on x minus 1, right, we get an undefined value at x is equal to 1, right. So now we want to find the value as we approach 1, not exactly 1, but as we approach 1. Okay, so now if you let x be 0.999 as we approach 1 from the left, right, we get something like, I think, 1.001. Okay, now approaching the limit x is equal to 1 from the right, right, so let's take 1.001, right, we get something like 0.999. Okay, so we can see that from these two values they are all surrounding, like they are all encircling 1. Okay, so by observation we can see that this limit, right, as s approaches 1 is equal to 1. But how can we solve it? Because it is not every function that we can actually look at, like in this example, that we can actually tell the limit. Okay, now that's where the limit concept is actually quite important. Now I will not only teach you the concept of limits, okay, I'll also be teaching you how to pass your exam. Like these two things are quite different. You can know the concept and you can't pass your exam, but you have to know the concepts to be able to make an A. At least if you don't know the concept you can get a C or D, but the concept, then how to pass your exam, this is actually very very important to me. Not everyone teaches that. Okay, so that's something that we would be doing a lot. Now, how can we solve this limit? Now, one way of solving limit is by factorization. Okay, now as I said, we would be going step by step. Okay, but let's use the factorization method to solve this. So now the limit as x approaches 1, right, how can we solve this? We can just factorize and get the answer 1. Okay, and this is just the basic way of solving limits to get what our eyes is telling us 1. Okay, but is this actually the best method to use? Now there's something called the right hand limit and there's something else called the left hand limit. Now having this graph, right, having this graph and having this function. Okay, now let's find the limit as x approaches, let's see. Okay, so let's label this 1, this as 2, and this as 3. So as x approaches what value should I take? Okay, let's say 1.5. Okay, 3 on 2. So as x approaches 1.5, right, we can simply, oh no, let me not use 1.5. I think it's not clear enough. Let me use something quite obvious. Okay, so let me use a straight line. Now let's label 1, this as 2, and this as 3. So as x approaches 2, right, we can simply map out the 2 on the graph, right, and bring it down, right? So this means that like x is approaching 2. So what's the value on the y-axis? So it's like the normal mapping of x values to get the y values. That's basically the concept of limit. We are actually finding the value on the y-axis. Now let me see if somebody has joined the class. Okay, so no one so far. Okay. So then, as I was saying, right, we have to find the left hand limit and the right hand limit. Now the left hand limit is the value of the limit when we come from the left hand side. Okay. Now one thing that you should know is that the value that we get from the limit when we come from the left hand side, and to see this clearer, right, we have to extend this line. Okay. Now the reason why I'm saying you have to extend this line either in your eyes or like in your sheet is just to make this clear, and we will solve more examples and see why you have to do this. Now to come from the left hand side, right, we are doing the left hand limit. So what is the value as x approaches to from the left, right, from this direction? What is the value as x is equal to 2? Now from this we can just map this up. So let's label the y-axis 1, let's label 2, let's label this as 3, right? So we can see that even though it's not drawn to scale, right, as x approaches to from the left, right, we can see that the value is equal to 1.5, right? 1.5 from the left. Now as x approaches to from the left, we can use some test values such as 1.999, 1.98, as close to 2 as possible, right, but not exactly 2. Now test values are not allowed in the calculation or solving of limits because it's not accurate. It doesn't work for all examples, so you can't use test values. Now in your math exam, if you use test values, like, you'll be marked wrong immediately. Okay, so test values are not allowed. But to check your answer, sometimes the test value is actually like makes you sure that what you've done is actually correct. So as you approach the limit from the left, right, so as I said, 1.998 to 1.99, right, you get a left hand limit. Okay, now, from the right, which is 2.110 or 2.00001, as close to 2 as possible, we get the right hand limit, right? So approaching 2 from the right. Now, with this example, it's clear and obvious that, right, the left hand and right hand limit, right, all approach their value, right, 1.5, because we're actually mapping on this value on the y-axis. Now, for a limit to exist, right, the left hand limit and the right hand limit must be equal. Now with this example, it looks clear and obvious that the left hand limit is equal to the right hand limit. But let's take this example, let's take this function, right, let's take this function, and take note that you not always have a straight line. No, it can be discontinuous. Do you get? So you can have something like this and something also going this way, right? And you are being asked to find the value of the limit. So let's label this as 1 and this as 2. The value of the limit as x approaches to from the left and 2 from the right. Okay, so let me label the y-axis, then we continue. So now approaching from the left, right, approaching from the left, as I said earlier, this is where the concept of extending the vertical line comes in. So when you extend the vertical line, right, it actually comes more visible what you are trying to do, right? So as you approach to from the left, right, you get the value, right? So where the vertical line meets the function from the left, right, you actually map this onto the graph, right? So you get something like 1.1, right, as you approach the as you find the limit from the left. Okay, because you draw the vertical line on the limit that you have been asked to find, right? And the same way we do with graphs, right? So you find the points where the graph meets the vertical axis, right? Then you map. So as you approach from the left, right, you get the value of y to be 1.11 or 1.2 or something. Do you see? So as x approaches to from the left, right, which is the 1.999 as close to 2 as possible, we get the value of y, right, to be equal to 1 point approximately 1.2. Okay, now as we approach to from the right, okay, which is denoted by 2 with the plus sign up here, right? Now what do we get? We are approaching x from the right, okay. So again, we look at the points where the function meets the vertical axis too, right? And we map it onto the y-axis. So let's label this as -1, -2, -3, right? So we can simply map this onto the y-axis, right? As, let's say, -1. So y is equal to -1. Now, for the limits to exist, the left hand and the right hand limit must be equal, right? So let's write the notation. So for the limit as s approaches a from the right, right, the limit as x approaches a from the right should be equal to the limit as x approaches a from the left. Do you see? So they should all give you a constant value. Let's call this L, okay, for the limits to actually exist. So if these two are equal, then you can come and conclude that the limit as x approaches a is actually equal to this constant value L. So this is the condition that we actually use to determine if a limit exists or a limit does not exist. So these two tests must be actually met. Okay, now this is the point that we actually go to the important examples. um Most of you haven't joined, so I won't introduce the some concepts that I think we have to take note of. You have to take note of everything, but there's a concept that I'll postpone to our Saturday class. So now I would like us to practice some questions, just one or two questions, not just any question, but I've actually selected some questions based on the slides and past questions and everything. Okay, so just 1 minute. Now, okay, so let's start with this. So find a limit, right, as x approaches to, right, of x squared minus 4 on x minus 2. Now this is a valid question in finding limits. Okay, now this is an example I would like us to take note of. Okay, now when you are asked to find a limit, right, there are, I think, four ways to do so. Okay, four ways to do so. Those are actually my ways that I have actually categorized them, and I think it works for solving every limit question. Okay, now looking at this, now the first thing that the first option that you should actually look out for is the method of factorization. Okay, now with this we can see that we can obviously factorize, right? We can obviously factorize. So we can factorize this as x squared minus 4. No, let's not do this. X minus 2, right? Multiplying x plus 2 on x minus 2. Okay. So we can cancel out our x minus 2 and we obtain x, the limit as x approaches 2, right? Of x plus 2. So you can find a limit as x approaches 2 from the right, right, which gives you x plus 2, right? So inputting the value of 2, you get the limit as x approaches 2 from the right, which is equal to 2 plus 2, and this is equal to 4. Okay, now you do the same thing for the left hand also, and of course you get 4. Okay, now for most questions, right, when you are not asked to find whether the limits exist. You'll not be expected to find the left and right hand limit. There are some questions that we actually would be doing when we meet in person, okay? But for now, to be safe, when you're asked to find a limit, just find the left and right hand limit and you are good to go, just to be safe. So from this, we can conclude that the limit as x approaches to from as x approaches to is actually equal to 4. So this is the first example, and one thing that I would like you to take note of is the factorization method. As I said, this is one of the four ways of solving limits. Okay, so let me clear this, then we continue. Nope. Now the second example that I would like us to take note of is this example. So find a limit as x approaches 3 of x cubed minus 27, right, on x minus 3. Now this is a typical example that you will be rarely be given in class, but it's easily examinable, okay, because they don't teach. It's actually lectures that we are actually given, and you are expected to go and find out um more ways to, like, to find out more understanding, right, on your own. Okay, now this is a typical factorization method that we are actually expected to know. So now, having this example, right, we can factorize this this factor, right, is of the form a cube minus b cube, which is equal to a minus b, right, multiplying a squared plus ab plus b squared. So you can write this down, okay? So using this formula, we can actually find the limit as x approaches 3, right, which is equal to, now our a is our x and our b is 3, right? So we have x minus 3, right, being multiplied by x squared plus 3x plus 9, right? So we divide this on the factor that we've been given in the question, right? X minus 3. So we cancel out, okay, and we get the limit as x approaches 3 to be equal to 3 squared, which is 9, plus 6 plus 9, right? So 9 plus 9 is 18. 18 plus 6 is 24, right? So we are actually done with this question. Okay, this is quite simple, right? Sorry, this is 3 times 3, so we get 9, and of course we get 27, right? Sorry for the mistake. So this is actually the second example that I would like us to take note of, and there is, as I said, there are four. I will be leaving one for our in-person class when we meet on Saturday. So this goes with the form the limit as x approaches 9, right, of x minus 3 on x minus 9, right? Now when you see a set, right, the best thing to do is actually to find the conjugate, right, and multiply to get rid of that set form that you have. So the conjugate of this set, right, is the root of x plus 3. So we multiply both the numerator and the denominator by the root of x plus 3, right? And we can easily cancel out this set, right? This just gives us 1, okay? So when we cancel this out, we get 1 multiplying the question, and we haven't changed the question by multiplying the set by the conjugates, right? It's the same thing. We are actually multiplying this by 1, okay? But we are doing this just to make the calculation easier, right? So the limit as x approaches 9, right, of this gives us the root of x minus 3, right, multiplying the root of x plus 3, the root of x plus 3, all on x minus 9, multiplying the root of x plus 3, okay? So now expanding this, we get the limit as x approaches 9 of x, right, plus 3x minus 3x, right, and of course gives us negative 9 on the denominator x minus 9 multiply the root of x plus 3. Okay, so this and this of course goes away and we obtain x minus 9 on the denominator x minus 9 multiplying the root of x plus 3, right? So this and this cancel out, giving us 1 on the root of x plus 3, right? The limit as x approaches 9 of 1 on the root of x plus 3, and this of course gives us 1 on the root of 9 plus 3, which is equal to 1 on 6. Okay, so this is the final answer that we get by solving this example. Now, one thing that I'd like you to take note of is that how should I put this? It's not about the examples, solving much examples, right? But the types of examples that we are actually solving.